Absorption refrigeration cycle. Ito na naman yung topic natin. Ito yung mga parts ng absorption refrigeration cycle. May absorber, generator, evaporator, condenser. Evaporator, condenser, ito yung basic refrigeration cycle. Ito naman yung heat rejection and heat addition sa generator and absorber. So they are evaporator and absorber, same pressure, and condenser and generator, same pressure. The absorption cycle. The basic absorption cycle is shown in figure 2. So ito, same ng cover natin. So yan nga yung sabi ko, same ang pressure. So dito nag-iikot yung video mo. So yung solution. Okay. So the condenser and evaporator are shown in figure 1. And the compression operation is provided by the assembly in the left half of the diagram. Andito yung vapor compression, compressor. Sa absorption, andito yung absorb vapor and liquid while removing heat. 2. Elevate pressure of liquid with pump. 3. Release vapor by applying heat. Ito yung absorption. So, high vapor. Lalabas dito is after ng is high pressure. Pupunta ng condenser, di ba? Then, expansion valve, then evaporator, then back to low pressure. So, ito mag-serve ng compression system mo yung ito na. Generator and absorber. So, dito magkano yung equivalent na compression system mo. So, absorption system na siya. So, dito yung refrigerant. Okay? So, ito yung solution. For example, dito, ang discuss natin is yung lithium bromide. Meron namang aqua ammonia sa ibang books. Tingnan na lang yung old yun. Yung bago ngayon is lithium bromide. So, marami pang combination. Iba kasi ang diagram ng aqua ammonia. Meron siyang analyzer. So, low pressure vapor from the evaporator is absorbed by the liquid solution. Yan, nagsimimix siya. In the absorber. If this absorption process were executed adiabatically, the temperature of the solution would rise and eventually the absorption of vapor would cease. To perpetuate the absorption process, the absorber is cooled by water or air that ultimately rejects the heat to the atmosphere. Ito. The pump receives low pressure liquid from the absorber and elevates the pressure of the liquid and delivers the liquid to the generator. And the generator, heat from high source temperature, ito added, drives off the vapor that had been absorbed by the solution. So, the liquid solution returns to absorber through a throttling valve whose purpose is to provide a pressure drop to maintain the pressure difference between generator and absorber. Kaya ang purpose lagi ng expansion valve. Expansion turbine, expansion process, kaya lang valve siya. Or throttling sinasakal. Now, the pattern for the flow of heat to and from the four heat exchange component in the absorption cycle is that the high temperature heat enters the generator while low temperature heat from the substance being refrigerated enters the evaporator. The heat rejection from the cycle occurs at the absorber and condenser. Yan. Dito yung dalawang heat rejection. And a temperature such that the heat can be rejected to atmosphere. Pag mas mataas yung temperature mo ng atmospheric temperature mo, hindi ka makaka-reject ng heat, di ba? Na for the performance, meron tayong coefficient of performance of the ideal refrigeration cycle. Meron din siya. So the COP, coefficient of performance of the absorption cycle, COP abs, is defined as the refrigeration rate divided by the rate of heat addition at the generator. Kasi ang may input mo yung generator. No, wala. Ito. The temperature ng source, TA, and TR refrigeration. Okay? Wait. Figure 3 suggests how to proceed with the analysis because the process in the box on the left consists of a power cycle that develop work needed to perform the compression of the vapor from the evaporator to condenser. So these two cycles are shown schematically in figure 3. The power cycle receives energy in the form of heat, Q sub G, at an absolute temperature T sub S, delivers some energy W in the form of work to the refrigeration cycle, and rejects a quantity of energy QA in the form of heat at a temperature T sub A. The refrigeration cycle receives the work W and with it pumps heat QA at the refrigerating temperature of TR to a temperature TA where the quantity QC is rejected. So this is equal temperature. Okay. Now the ideal cycle operating with thermodynamically reversible process between two temperatures is a Carnot cycle, which appears as a rectangle on the temperature entropy diagram. For the power cycle on the left side of figure 3, U sub G over W is equal to TS over TS minus TA. And for the refrigeration cycle on the right side, figure 3 is QA over W is equal to TR over TA minus TR. The refrigeration rate is QA and the rate of heat addition at the generator is QG. Use the expression for QG and QA respectively. The COP is equal to QA over QG, or W TR over TA minus TR times TS minus TA over W over TS, or TR times TS minus TA over TS divided by TA minus TR. Yan yung equation ng COP para sa absorption cycle as ideal. So example number 1. What is the COP of an ideal heat-operated refrigeration system that has a source temperature of heat of 100C and a refrigerating temperature of 5C and an ambient temperature of 30C, given T sub R 5C, small letter kasi given is hindi absolute. T sub S is equal to 100C, T sub A is equal to 30C, required COP. Solution, ang COP is equal to TR times TS minus TA divided by TS of times or divide by TA minus TR. So COP is substitute ng value. Yung difference, okay lang na wag mo na i-convert sa absolute both. Kasi difference na siya. Okay? Yung capital letter sa yung TR na hindi difference, so yan ang i-convert mo na lang. So that is 5 plus 270.15 times 100 minus 30 over 100 plus 270.15 over 30 minus 5 is 2.09. Okay lang, magiging mong 273 ito. Okay? Kasi whole number naman to. Okay? Pag this is 5.15, so gawin mo 273.15 para di maapektuhan yung yung value. So this pwedeng 5.1, mag-ano ka rin 273.15 kasi ito yung accepted value. Pag may decimal ka dito, or 273. Huwag 273.1. So, yun yung example. Several tests are detectable. A, as TS increases, ito, the COP increases. As TR increases, the COP increases. As TA increases, the COP decreases. Yeah. So, yan. Now, temperature pressure, concentration, properties of lithium bromide water solution. So ito yung i-discuss natin. Ano yung saan mo kukunin yung mga properties. So lithium bromide is a solid salt crystal. In the presence of water vapor, it will absorb the vapor and become a liquid solution. So pag nag-mix siya sa water vapor. Okay. So ito yung ano mo is water. Ang refrigerant mo is water. So ang solution mo is lithium bromide. The liquid solution exerts a water vapor that is a function of the solution temperature and the concentration of the solution. So yun lang yung concentration plus the temperature ma-form ng ibang properties. If the two vessels were connected as in figure 4, one vessel containing lithium bromide solution and the other pure water. So, each liquid would exert a water vapor pressure at the water vapor pressure exerted by two liquids will be equal. So this pressure is equal. An example of one equilibrium condition is noted in figure 4. If the temperature of pure water is 40 C, its vapor pressure is 7.38 kilopascal. So the same vapor pressure would be developed by lithium bromide solution at the temperature of 80 C. In concentration, X is equal to 59% lithium bromide on a mass basis. Many other combination of temperature and concentration of solution also provide a vapor pressure of 7.38 kilopascal. So figure 5 is a temperature pressure concentration diagram for lithium bromide water solution. So dito yung mga graph na gagamitin natin. So meron siyang lithium bromide in solution, percentage by mass, and the saturation temperature of pure water degrees C. This is the solution temperature 120 C. So any combination, saturation temperature, and saturation temperature, so makukuha mo yung percentage by mass ng lithium bromide. Concentration is the abscissa of the graph, and water vapor pressure could be considered the ordinate as shown on the vertical scale on the right. For convenience, the saturation temperature of pure water corresponding to this vapor is shown as the ordinate on the left. Kasi ito yung saturation, di ba? May equivalent temperature siya. The chart applies to saturated conditions where the solution is in equilibrium with the water vapor, as in vessel and the right on figure 4. The first stage in analyzing the simple lithium bromide absorption cycle can now be performed by using the property data in figure 5. So other combination ng ano nito, ng solution and refrigerant, may kanya-kanyang table siya o figure. So example number 2, compute the rate of refrigerant water through the condenser and evaporator in the cycle shown in figure 6. If the pump delivers 0.6 kg per second and following temperature prevail. So the generator 100 C, condenser is 40 C, and evaporator 10 C, and absorber 30 C. So yan, given pump 0.6 kg per second, nag-iikot, so W yan. Generator 100C, condenser 40C, evaporator 10C, absorber 30C. Yan lang mga given mo. Required, what is the refrigerant flow in this problem? So LS is M3. Yan. M3, M4, M5. Okay? Ito naman, iba naman to. So, yan. Dito, so nawawala doon, ibabalik nito. Kaya dito lang is, itong solution mo is yung lithium bromide lang. So, calculation of mass flow rates in, wait. Ayan, tama. Same title pala. So, solution. Okay? So, this is from the book then. So, pag nag-solve kayo, pwede nang wala itong mga kwento-kwento. Since a saturated condition of pure water prevails in the condenser, due to simultaneous existence of liquid and vapor. The condensing temperature of 40C fixes the pressure in the condenser and thus in the generator of 7.48 C. So parehas ang pressure niya. From a similar reasoning, the evaporator of 10 C establishes low pressure at 1.23 C. So parehas din ang pressure niya. So figure 7, so ito na yung is a skeleton of PXT diagram extracted from figure 5. So sa figure 5, so yan nga, di ba? 100C and ano, pressure 1.23, 7.30 at yung katapat niya 10 and 40. So line niya yan. So the solution leaving a component is representative of the solution in the component. So the state point of the solution at point 2 leaving the generator is found from figure 7 at the intersection of the solution of temperature of 100C and pressure of 7.38 kilopascal. This concentration is X2 is 0.664. So pagbasa nyo, so yung 40C and 100C solution dito, ang lalabas mong concentration is X2 is 66.4%. And leaving the absorber at a solution temperature of 30C and a pressure of 1.23 kilopascal. So yan ang labas mo is 0.5 or 50% concentration. Okay? So nakuha niya ng paggamit ng figure. Now the two mass flow balances can be written about the generator, which is total mass balance flow M2 plus M3 is equal to ito, M1. Diba? So total siya. Ano lang siya dito. So lithium bromide balance, siyempre yung M1. So ito, M1 times X1 is equal to M2 times X2. So kung ano yung lumabas dito, siyempre meron, multiply mo ng S2, yun yung lithium bromide mo. So paglabas dito, nag-iba na yung percentage mo. So equal din siya sa pinasok mo solution kasi ito pure water. Okay, solving the two balanced equations simultaneously give M2 is equal to 0.452 kg per second and M3 is 0.148 kg per second. Approximately 4 kg of solution is pumped for each kilogram of water vapor develop. Paano? 0.452 divided by 0.148 is approximately 4. Yan. So, nakuha mo na yung pagkuha ng masses. Now, for the enthalpy, kasi kukuha natin yung mga work, yan, heat, kailangan natin ng enthalpy. So, in order to perform, dito makakuha sa figure 8. Di ba? Ano naman yung percentage ng lithium bromide tapos solution temperature. Ito yung enthalpy ng solution. So in order to perform thermal calculations on the absorption cycle, enthalpy data must be available for the working substances at all crucial position in the cycle. So sa ibang combination solutions, meron sa mga handbook, ibang books, meron sa Paris yata, meron din to. Paris Chemical Handbook. Water and liquid or vapor form flows in and out of condenser and evaporator. So, enthalpies at this point can be determined from the table of properties. Enthalpies at each point. Okay? So, in the generator and absorber, lithium bromide water solutions exist for which the enthalpy is a function of both temperature of the solution and the concentration. So, figure 8 presents enthalpy for lithium bromide water solution. The data are applicable to saturated or subcooled solution and are based on zero enthalpy of liquid water at 0C and a zero enthalpy of solid lithium bromide at 25C. So, kaya pag gumamit kayo ng English units, sa English units ka lang gumamit ng figure. Dito, properties niya. Kasi baka doon, 0 Fahrenheit ang base. Diba? So, kaya mag-iba ang, pag kinonvert mo, iba. Since the zero enthalpy for the water in the solution is the same as that in conventional table properties of water, system tables, the water property tables can be used in conjunction with figure 8. So, gagamitin mo lang yon dito sa 3, 5, 4. Pagdating dito sa 2 and 1, so itong gagamitin mong dalawa. So, thermal analysis of a simple absorption system. So, example number 3, continuation to. For the absorption system of example number 2, shown in figure 6, compute QG, QA, QC, and QE. As a figure. So, given, as in example number 2, required QG, QA, QC, and QE, and the COP. Solution, ito yung mga flow rates na nakuha sa example number 2. M1 is 0.6 kg per second. M2 is 0.452 kg per second. M3 is equal to M4 is equal to M5 is 0.148 kg per second. X1 is 50%. X2 is 66.4%. Now, enthalpies of the solution can be read of figure 8. So, H1 is equal to H at 30C and X 50%. So, 50% and 30C. This is negative 168. Hindi lang makuha sa tingin niya na negative 168 na. Ano nyo, ilinyaan nyo, tapos hanapin nyo yung value. Ruler. H2 is equal to H at 100C and X 66.4 or negative 52. 100C. 0.664. Ito. 65. 67.5. Mga dito, mga 100. Yan. So, negative 52. Yan. Okay. Enthalpies of water, liquid, and vapor from steam table. So, ST is equal to H of saturated vapor at 100C. Sabi mga saturated lang. So, 2676 kJ per kilogram. H4 is equal to S of saturated liquid at 40C is 167.5 kJ per kilogram. Now, the rate of heat transfer at each component can now be computed from energy balances. So, QG is equal to M3H3 plus M2H2 minus M1H1. Kita nyo sa heat balance nito. Diba? Ito, importante yung arrow. Huwag kayong drawing ng walang arrow. So, ito out, out. Kaya nag-add yung 3 and 2. Minus, yan. Kasi yung mag-a-add din ito Q3 plus M1H1. Yan. Equals M3H3 plus M2H2. Diba? It balance. So, QG is equal to 0.148 times 2676 plus 0.452 times negative 52 minus 0.6 times negative 1.168 is 473.3 kilowatts. Then QC, saan yung QC? Yan. Is M3H3. Ito pala. Minus M4H4 is 0.148 times 2676 minus 167.5 is 371.2 kilowatt. QA, dito, ayan. Dalawang pumasok, isang lumabas to sa 1 and QA. So, ito minus 2 is equal to QA. So, M2H2 plus M5H5 minus M1H1. 0.452 times negative 52 plus 0.148 times 2520 minus 0.6 times negative 168 is 450.3 kilowatt. Then next, QA is equal to M5H5 minus M4H4. QA is equal to 0.148 times 2520 minus 167.5 is 348.2. So finally, COP is equal to QA over QG is equal to 348.2 over 476.6 or 0.76. So yan ang value ng ng COP sa absorption cycle. Maliit, hindi sa mga 3, 4, yan. Ito typical values niya. Huwag kang sasagot ng 5, 3, yan. Bawal yun. Okay? So next is the absorption cycle with heat exchangers. So mga variations na to. So yan, ang istura. So an examination of the simple cycle in operating temperature shown in figure 6 reveals that the solution at point 1 leaves the absorber at temperature of 30 C and must be heated to 100 C in the generator. Similarly, the solution at 0.2 leaves the generator at 100 C and must be cooled to 30 C in the generator. So, may improve yung performance mo. One of the major operating costs of the system is the heat added in the generator QG. So liliit siya. And realistically, there will be some cost associated with the removal of heat in the absorber. Liit din yun. A logical addition to the simple cycle is heat exchanger as shown in figure 9 to transfer heat between the two streams of solution. This heat exchanger heats the cool solution from the absorber on its way to the generator and cools the solution returning from the generator to the absorber. So example number 4. The simple cycle operating at temperature shown in figure 6 is modified by the insertion of a heat exchanger as shown in figure 9 such that the temperature at point 2 is 52 C. Ito, given siya. The mass rate of flow delivered by the pump solution is 0.6 kg per second. What are the rates of energy transfer at its one of the component and COP abs of the cycle? So given figure 6 is figure 9. At point 2 is 52 C. Solution pump flow rate is 0.6 kg per second. Required rates of energy transfer at each of the components and COP abs. Baka maging COP abs. Yan. Okay. Nadoble lang pala. Wait, ulit. Okay, solution from examples number 20, M1 is equal to M2 is 0.6 kg per second. M3 is equal to M4, 0.452. So dito na-apektuhan na sa enthalpy lang ito makaka-apekto yung 52C. So M5, M6, M7 is 0.148 kg per second. The enthalpies that remain unchanged are so ito yung mga enthalpies na hindi na bago. H1 is negative 168 kJ per kilogram. H3 negative 52 kJ per kilogram. H5 is 2676 kJ per kilogram. H6 is 167.5 kJ per kilogram. H7 is 2520 kJ per kilogram. Now, the heat transfer rate at the condenser and evaporator remain unchanged. So, QC is 371.2 kilowatt and QE is 348.2 kilowatts. Hindi na bago. Mababago lang ito. Kasi nagbawas nga. Mababawas to, mababawas to. So the temperature of 50% solution leaving the exchanger at 0.2. So, nyo. This is 50% solution. And the solution at that condition has an enthalpy of negative 120 doon sa chart as properties. Enthalpy as indicated by figure 8. The rate of heat absorbed by the solution passing from the absorber to the generator is QHX is M1 times H2 minus H1 is equal to 0.6 times negative 120 minus negative 168 is 28.8 kilowatts. Since this same rate of heat transfer must be supplied by the solution that flows from the generator to the absorber, QHX is equal to 28.8 kilowatt. That is equal to M3 times H3 minus H4. So 0.452 times negative 52 minus H4. And so H4 is negative 116 kJ per kilogram. So nagbago to. Ha? Ito hindi. So figure 8 shows that 66.4 solution with an enthalpy of negative 116 kJ per kilogram has a temperature of 64 C. So yung 116 na yun, negative 116, ang percentage solution niya is 66.4. Now, the temperature, makukuha mo naman sa figure 8 is 64 C. Yan. The rates of heat transfer in the generator and absorber can now be computed. So Qg is equal to M5 H5 plus M3 H3 minus M2 H2 is 0.148 times 2676 plus 0.45 times negative 52 minus 0.6 times negative 120 is 444.5 kilowatt. And QA is equal to M7 H7 plus M4 S4 line minus M1 H1. So QA is equal to 0.148 times 2520 plus 0.45 times negative 116 minus 0.6 times negative 168 is 42.1, 421.3 kilowatt. Now, the coefficient of performance of the system that incorporates the heat exchanger is COP abs is QA as per QG is 348.2 over 444.5 is 0.783. So this COP is an improvement over the value of 0.76. So tumaas, di ba? Yung COP mo. Applicable to simple system without a heat exchanger. Okay, next. Configuration of commercial absorption system. Ito yung commercial. Ano yung mga nandyan? Okay? Ano yung paano mo arrange sa equipment? The construction of commercial absorption plant taking advantage of the fact that the condenser and generator operate at the same pressure combines this component in one vessel. Yan, isang vessel siya. Similarly, since the evaporator and absorber operate at the same pressure, this component likewise can be installed in the same vessel. So, in high-pressure vessel, dito, the water vapor from the generator drips to the condenser, where it is liquefied, while in the low-pressure vessel, the water vapor released at the evaporator flows downward to the absorber. To enhance the transfer rate at the evaporator of a circulating pump sprays the evaporating water over the evaporator tubes to chill the water from the refrigeration load. Note that the chilled water serving the refrigeration load is a separate circuit from the water serving as a refrigerant in the absorption unit. Siya. Ito yung system niya talaga. Hindi yung iba na nakikita nyo mga thesis na ginagawa ko, may mga ducting pa, yung ano-ano pa. So, magbasa kayo. Magbasahin lang sa mga reference na ginawa na dati. Yung kasi di yung binasa, nag-invento lang, trial and error lang sila. So, maintaining separate water circuit helps maintain better purity in the absorption unit and permits the water serving the refrigeration load to operate at pressure above atmospheric. Another picture shown in figure 10 is that the cooling water from the cooling tower passes in series to the absorber and condenser, extracting heat in both components. So, in the photograph of the absorption unit, ito, an absorption unit of 1,200 kilowatt cooling capacity. So, yan yung mga checkness, yung mga brand. The high and low pressure vessels can be distinguished. The high and low. It is also possible to combine all the components into one vessel with an internal separator between the high and low chamber. Kasi magkaibang pressure. So, double effect system. So, ayan naman, palala ng palala. So, double effect. Ano ba yun? Generator, condenser, absorber. Absorber naman. Tapos, yan. A lithium bromide absorption unit with improved efficiency is the double effect system shown schematically in figure 12. The major distinguishing feature of the double effect system is that it incorporates a second generator. 2, which uses the condensing water vapor from the generator 1 to provide its supply of heat. So, heat sa ano yung condensing water vapor. Yan, check nyo doon. May sa compilation ko meron doon solution to. Yung isang problem yata doon. There are 3 different levels of pressure in each of the vessels shown in figure 12 kasi double effect. May gitna. And the medium pressure steam of the order of 1000 kilopascal is supplied to the generator 1 instead of low pressure steam approximately 120 kilopascal supplied to the generator in a single stage unit. High pressure to. The lithium bromide solution from generator 1 passes to a heat exchanger, which is transfer heat to weak lithium bromide solution on the way to generator 1. So the solution that passes onto generator 2 is heated there by condensing water vapor that was driven off in generator 1. The solution next passes to a restriction which drop the pressure to that of vessel 2. Following reduction of pressure, some of the water in the solution passes to vapor, which is liquefied in the condenser. So, the double effect absorption unit operates with higher COPs than a single stage, as shown in figure 13. So, ito yan. Single effect, double effect, very high. Okay? Times 2. Figure 13. Ito yung COP of single stage and double effect absorption unit. Yan. Train company. May mga trains in the... Ayan. Now, steam-driven combination with vapor compression. Ito naman. Okay. Some large capacity water chilling installation use an energy source of high pressure steam in a system that combines a vapor compressor and an absorption system. So, high pressure pupunta sa steam turbine, idadrive niya yung compressor. So, ito yung vapor yung compression unit. So, yung water to be chilled, masi-chill sa evaporator. Then, yung low pressure ito, ay yung dadrive sa generator ng absorption unit. Then, pupunta ang evaporator naman niya is yung continuity na tong water to be chilled. Okay? Sa evaporator to. Ito yung lithium bromide solution or absorption unit. Yan. The high pressure steam, as in figure 14, first expand to a turbine which provide the power for driving the compressor of the vapor compression system. The exhaust steam from the turbine passes to the generator of the absorption system. Yan. The water to be chilled passes in series to the evaporator of the two refrigerating plant. This combination is the counterpart of the type of power plant where some of the high energy pressure steam is used to generate power and condensation of the steam is used for heating or process purposes. Yan. Parang ganon yun. Pwede naman tong may turbine dyan, kumuha ka ng steam, isa dito tapos continuous na dito. Pwede ito galing sa isang boiler. Okay? Tapos power naman doon. Parang cogeneration. Next, ito na yung isa, aqua ammonia. Okay? Yung example nito sa ibang book meron. Other pairs of substances can also function as absorbent and refrigerant. That is water as absorbent and ammonia as the refrigerant. Ito yung mga luma. This combination called aqua ammonia was used in absorption system years before the lithium bromide water combination became popular. Kaya ang example dito is lithium bromide. The aqua ammonia system shown schematically in figure 15 consists of all the component previously described: generator, absorber, condenser, evaporation, and solution heat exchanger plus a rectifier and analyzer. So, ito yung additional niya sa aqua ammonia solution. So the need for them is occasioned by the fact that refrigerant vapor released at the generator, the ammonia, contains water vapor as well. When the water finds its way to the evaporator, it elevates the temperature there. To remove as much water vapor as possible, the vapor driven up the generator first flow countercurrent to the incoming solution in the rectifiers. Yan ang purpose. Next, solution passes through the analyzer, a water-cooled heat exchanger condensing some water-rich liquid, which drain back to the rectifier. A small amount of water vapor escapes the analyzer and must ultimately be passed as liquid to the evaporator. In analyzer, binabalik nito. So, liquid ang ano doon. A comparison of aqua ammonia and lithium bromide system follows. The two systems have comparable COP. The aqua ammonia system is capable of achieving evaporating temperatures below 0 C, but lithium bromide water system is limited in commercial units to no lower than about 3 C. The aqua ammonia has the disadvantage of requiring extra component, but does have the advantage of operating at pressures above atmospheric. The lithium bromide water system operates at pressures below atmospheric, resulting in unavoidable leakage of air into the system, which must be purged periodically. Special inhibitors must be incorporated in lithium bromide water system to retard corrosion. So, yan. Okay? So, this is the end of this topic. So, ito naman yung mga diagram from internet na.